In our last video, we defined limit for functions on two variables. In this video, I actually want to evaluate these three limits. And as I look at them, I'm thinking, well, I know a lot of stuff about limits from Calc 1, and these remind me of those limits. Something in the domain is getting closer to a point. What does the function do? And if I was in Calc 1, I would really want to be using my limit laws here, right? The rules that say, hey, if you're taking a limit of a fraction, you can take the limit of the top and bottom independently of each other, and that you can split up differences and that powers and roots behave very well. And the good news is all of those rules still hold. This is a theorem from our textbook. The following rules hold if L, M, and K are real numbers, and we have these two limit statements. Sums, take the limit of a sum and you add the limits. To take the limit of a difference, you subtract, and everything works out exactly the same way. So in this first problem, I can imagine taking the limit of the top and the limit of the bottom separately from each other, and then splitting up around the differences. And then for this term, I would take the limit as xy approaches 4, 1 of x, and then square that, right? I could just work it all the way out. But having had that experience in Calc 1, I'm feeling pretty good about just thinking about plugging in the values for x and y, because I'm not dividing by 0. I'm not doing anything bad. So on the bottom here, I'd have 2 minus 1. On the top, I would have 16 minus 4. 12 divided by 1 is the real number 12. So as we get closer and closer to the point 4, 1 in the domain, the z values are getting closer to 12. Okay, now I move on down to the next problem and I realize, I'm dividing by 0. And if I just try to evaluate everything, it's one of those 0 over 0 kind of indeterminate forms we remember from Calc 1. Now what's cool about those is those don't always behave the way we might think, and we need to take a moment here, because when you heard me say indeterminate form, a lot of you thought about L'Hopital's rule. We don't have a L'Hopital's rule for functions on more than one variable, and we don't even know what it means to take a derivative of a function on two variables. So right now we need to think about limit laws. We need to think about taking the limit of the top and bottom separately. So the way through this problem is algebraic. We need to simplify that algebraic expression so that we're no longer dividing by 0. Pause the video here, write this algebraic expression down, and see if you can simplify it to cancel off the root x minus root y. Okay, I actually want to do this twice. I want to simplify this algebraic expression two different ways. I'm hoping that a lot of you, when you were given that chance to simplify it, thought about multiplying by the irrational conjugate of the bottom, right? Giving me the x minus y. This is the root x plus root y that I multiplied by, and then if I factor an x out of these terms, I see the x minus y's cancel. And after I do that arithmetic, I can actually rewrite my limit as the limit as my point gets closer and closer to the origin of x times root x plus root y. Well, the limit laws say I can take these two limits independently of each other and multiply them together, really just giving me the power to plug in everything because I'm no longer dividing by 0. And I get 0. Okay, the other way I know how to do that arithmetic, and it doesn't matter that I'm doing it now rather than before, right? Any way to do this arithmetic is fine, is just by factoring. I can factor the x out, and then I can factor the x minus y as if it were the difference of two perfect squares. And again, I see that the root x minus root y's cancel out, leaving me with just x times root x plus root y. We can use either approach and it doesn't matter. And on this problem, I have the limit as xy is approaching now 1, 1, and I have that same expression simplified. And if I plug 1, 1 in there, I'll get 2 times 1 is 2. This reminds me that when I have that 0 over 0 form, functions can behave weird at those points and behave differently for every example. That's why we called those indeterminate forms.